Alright, today's problem is subarray sum equals k. They give us an array and they give us a target sum of k, and here you can see that we have a subarray here with a sum of 2 and a subarray here with a sum of 2. So 2 subarrays in total, so our output is 2. So in this example here, if the sum is 2, our answers will be here we have 2, here we have another subarray with a sum of 2, so 0 plus 2 is 2, and then finally we have this outer subarray with a sum of 2. So 3 answers in total. Now how do we find these 3 answers without checking every single possible subarray? Because if we check every single possible subarray, that is an O of n squared operation. So what we want to do here is just keep a running sum. So let's see what happens if we keep a running sum from the very leftmost. So we have -1 here, and then if we do -1 plus 0, we can expand it to -1 again, and then -1 plus 2 means that this subarray sum has a value of 1, and then finally 1 plus 1, this subarray sum has a value of 2. So here we find one of our answers, but that's because it started leftmost on the very left. What about these 2 answers here, right? These 2 answers where it was a subarray, in the middle of the array. And you can see that these 2 actually slot really nicely. So this subarray here fits in right here, and this subarray here fits in here. Now, the relationship that we see here is the fact that if we have something like sum that we're calculating, and we want to see that if maybe it's possible that there's a subarray of k that's possible here, all we have to do is see, have we seen any subarray with a sum of x yet? So for the example here, we have that sum is equal to 1, k is equal to 2, and our question becomes, have we already seen a because this subarray is shorter, so that means we have seen it before we see the bigger one. So have we seen any where k is equal to, and in this case, -1, because -1 plus 2 is going to give us 1. So here the answer is yes, we've seen this one and this one, which means each subarray that we've seen before can create a subarray of 2 by taking the difference between, this sum and this x here and this x here. Okay, so that would bring our total up to 2. And then on our last step, as we're continuing our algorithm this way, we'll see that for the last one, this also gives us a subarray sum of 2, so we get our grand total of 3 to finish the algorithm. Okay, so that's the intuition. If we want to actually code it, let's see. Well, first, how do we solve for this x? This is going to be, x is going to be equal to sum minus k. And we want to do this check at each step, right? So for example, when we're going down, when we're checking, let's say this -1, we would have said, -1 minus 2 means that x equals -3. And we would have to check, have we seen -3 before? And if so, then, -3 and -1 would mean that there's a subarray that's possible here with a value of 2. Now, obviously, we haven't seen a sum of -3, but how do we keep track of that? So here's where a map will come in handy. So we want to have some sort of a map that counts from the sum to the count. So if we copy this over, let's see. We'll do that. Copy it here. And you can see as we're going through our algorithm, we just need to keep track. So -1, we've seen it once. Now we're here, -1, now we've seen it twice. And then here we query for does -3 exist? And the answer is no, so we continue. And now we have 1, we've seen it once. And here what 1 is going to query is, have we seen -1? Because that's what would make these k equals 2 subarrays? And the answer is going to be yes, we've seen 2. So that means now our total is up to 2. And then finally here, at 2, that'll bump it up to 3. Okay, let's try coding this out. Right, so let's create a map first. We'll use a hash map. And we'll see at the end that we can actually replace this hash map with a normal array. But first, let's use a hash map. So this will be our count map. And we need some sort of a way to keep the running sum and some total. So we'll return this total at the end. Okay, so we have for int, n, and num. So we read every single number. Sum plus equal n. And if this sum happens to be k, then that's an answer, so we'll keep track of it. Otherwise, let's see if we've seen a pass interval x that can form a subarray of k. So like we said before, int x is going to be equal to sum minus k. So what we'll do is we'll check if count map, if we've seen k before. Then what we'll do is total will be plus equals countMap.get x. So this is the case of we've seen 1 and we ask have we seen -1, and yes, we've seen it twice. So we add these two answers into our total count. Okay, but this call wouldn't work if we never put anything into the map. So let's put something into the map. So count map, we're going to put our current running sum so that future sums can use us, right? So count map.put sum, and we'll get whatever count map.get sum is plus 1. Now we have to watch out here because get sum, if we've never put something in it before, will return null. So what we want to do here is get or default, and then have this default value of 0. Okay, let's give this a try. Cool, so it's accepted, and this should, like put us around like 95% in terms of like how fast it is. But how do we get that last 5%? Well, there's a constraint that we haven't been using, which is the length of the array is in 20,000, so 1 to 20,000, and the number is from -1,000 to 1,000. So let's see how we can use these two to our benefit here. So we have these two facts. And what I'm interested in is, can we replace this, this complex data structure hash map with something very simplistic, which is just an array? So can we replace hash map with an array? So with an array, what we can do is, for example, if we have A, we'd say 0, 1, 2. And what this would just mean is like if you have a sum of, 3, we've seen it 1 time. We have a sum of 4, we've seen it 2 times. So this just replaces the hash map representation of 1, we've seen it, or 3, we've seen it once, and 4, we've seen it 2 times. Okay, so let's see, is this possible? So the thing that we're worried about here is that maybe we'll need an array so big that there's not enough memory to keep it all, in memory. So let's see. We use count map to store our sum. So what's like the biggest number that we would have to index? What's going to be the biggest sum that is possible? So imagine if we had something like an input array like -1,000, and then 1,000, 1,000, and then we continue this all the way to 20,000. So this has an array of length 20,000. Then we would need a way to index everything from -1,000 all the way up to 1,000 times 19,999. So we need a way to index all of these possible sum. For simplistic reasons, let's just round off and say it's 20,000 times 10,000. So that's going to give us 1, 2, 3, 4, 1, 2, 3, 4. Oh, sorry, not 20,000. This is 20,000 times 1,000. So remove a 0. That means we need to store around 20 million elements. Okay, so now the second thing we have to figure out is what type of element are they? So usually we use an int array, but can we use something that's a little bit more space efficient? And the constraint we're going to use here is the length of the array is 1 to 20,000. So how many times will we need to increment an element? Well, you see here in our for loop, we increment it by 1, or at most by 1, and we do that for every single element. So if by some magic miracle, they're all zeros in our input array, and we keep incrementing that we've seen 0, we'll only increment it up to 20,000 times. So a at I is at most 20,000. So if we look at the primitive data types of Java, you can see that short is 16-bit and holds up to, let me zoom in here. So short holds up to 32,000, whereas int holds up to this big number here. So we don't really need an int, we only need a short, and that means from space-wise, from 32-bit, we get reduced down to 16-bit. So what we'll do is we'll have a short array instead, and let's assume the worst case that we need 20 million of shorts. So we'll have 20 million times 16 bits, and then from here we can divide it by 8 to get bytes, divide it by 1,000 to get kilobytes, divide it by 1,000 to get megabytes, and that is going to give us around 40 megabytes. So that means in the worst case, we're going to have an array that consumes 40 megabytes of memory. It's pretty bad, but it's not too bad that I wouldn't, say that this is an impossible solution. So let's try coding it out. So we don't have to go for the worst case. If we sacrifice one pre-processing loop, what we can do is we can find out everything that we have to index. So we have to index everything from min sum all the way up to max sum. So what's the minimum sum that we can get in our running sum, and what's the maximum sum we can get in this variable sum here. So let's do our pre-processing loop. We'll have a min sum and a max sum, and then we'll just have a if condition here. So that way we can read these two without worrying about out of bound errors. And then now we'll keep track of an actual sum. And if sum is less than min sum, if sum is greater than max sum, we can overwrite max sum. Okay, so at this point, we know exactly how big of a short array we need to be able to index every possible sum that we'll encounter in our algorithm. So we're going to have a short count map, and it's going to be equal to new short max sum minus min sum plus 1. So an example is, let's say your min sum ends up being -1 and your max sum ends up being 2. Then that means you have to be able to index everything from -1, 0, 1 to 2. So you have an array of this size, which has a size of 4. So that's going to be 2 minus -1 plus 1, which is what we have here. Okay, so that replaces our count map. Now the second part we have to look at here is here we try and check to see if it contains key. And you can see that this sum here, it's possible for this to be negative, as we've seen in our example here. Here we have a negative sum, but we can't index into negative into our array, which means we need some way of converting between this key, which is the sum, into the actual index of our array, which is going to be 0, 1, 2, 3. And the equation here is that we have our key. If we minus the min sum, so if we minus some sort of offset, we're going to get I back. And this offset is going to be equal to our min sum. So for example, let's say we want to increment that we've seen -1 once. We'll do -1 minus -1 because our offset is our minimum sum. So our minimum sum kind of shifts where the start of our array begins. So we need to minus the offset to get back to I. So that will give us 0. And you can see that this works even if our min sum is positive. So that's why we have 2 and max sum of 5. So now we have 2, 3, 4, 5 with an array like this. And suppose again that we want to index into this 4 here. That's going to be 0, 1, 2, 3. And then what we'll do is we'll do 4 minus the minimum sum, which is 2, is equal to 2. So that will give us the correct I index here again. Okay. So here we have our index. Let's see if we've seen a pass interval. And then if so, we can total plus equals count map at x minus min sum, which is our offset. Okay, there's another optimization we can do here. So we know if we've seen this x, if it's between the bounds of our min sum and max sum, right? If it's outside, then there's no way we'll ever see a subarray sum of that size. So what we'll do here is if x is greater than or equal to min sum and x is less than or equal to max sum, so we'll do this check because anyway our array only holds these sum to be available to be indexed anyways. So we'll do this check and then we'll increment it. And now instead of put, we can just do count map at sum minus min sum. So again, the min sum is our offset. And we'll do plus plus. Now this line here, we don't have to put a guard like this because we designed our count map to be able to handle all possible sums by doing this pre-processing step beforehand. Okay, so now we've successfully replaced our hash map with a simple array. All right, so we have to get rid of this now because we've already defined it earlier here with InSum. Okay, it's accepted. And there's that 100%. So this is going to be the HashMap solution, and this is going to be the brute force n-squared solution around here. All right, that's it for today, and I'll see you on the